Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are five modules. Now we'll be adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more.
Hello friends, welcome to my fourth class in this series of classes in Physics 1. As I mentioned often that it's common to all course, all students at the BTech level have to learn, because physics is is something you are learning in your own engineering program. It's all physics, all of them are based on the fundamentals of physical sciences. So in our course, some students have to develop some fundamental knowledge in first year, so that those ideas become building blocks of whatever you learn in future. So you have kept topics which are which will be essential to learn anything you study in your own courses. It may be the studies of semiconductors. It may be the study of the storage materials. It may be the study of X-rays for biomedical students. It may be the study of quantum computations for computer science and IT students. It may be the study of electrical devices, where the basic electromagnetic theory, okay, which is studied as a field theory paper or EM theory paper in electronics courses. So in physics courses, we are trying to offer the fundamentals of all those things you learn. So in this fourth class, what we have done in the past three classes, I have actually identified where we begin. Where we begin? We begin with the most modern topic of physics, that is called quantum mechanics. Quantum mechanics you are learning in two steps. Part 1 of quantum mechanics is you are learning in first year, and part 2 of quantum mechanics, which all of you again have to learn in the second year courses, because quantum mechanics is the language of learning the most modern physical phenomena. In first year, we basically develop some theory. The theoretical background of the of everything is done. Just like in classical physics, the first thing you learned in mechanical system is Newtonian ideas. So similarly, first you have to know the theoretical background of this quantum mechanics concept. Okay, came up in 1900 from the explanation of the experiment of black body radiation. And starting from 1900 to 1927, few wonderful experiments have done. Each experiment at the end of the day is going to give you one new idea. Okay, and at the end of first year, you will jot them down so that you can apply them in solution of actual problem. Okay, suppose how I often mention how electron moves in a metal, how we explain journey of electron or hole across the junction of a semiconductor. All these are basically quantum mechanical phenomena. So how you explain them? Okay, how do you solve this problem? You can only solve them if you know the theory now. So all those solution we will do next year. Now I am offering theory. And what I did, I started with Max Planck, okay, the father of quantum ideas. And we went back to 1900 and we tried to know what Planck is doing in 1900. Okay, what Planck is doing. So let us explore. And what is today's class? Okay, you see, Last 2 days, actually, I was focusing on telling what is black body, what is the experiment with black body, okay, what is the observation of the experiment, what you have to what is the essential outcome of the experiment, okay, all those things. But as I mentioned earlier, the concept of black body radiation itself is a part of thermodynamics. So today we'll try to explore with Planck how quantum mechanics comes into business, because today's class is very vital, because this is going to give you first quantum concept. That is how you can the concept of quantum mechanics is coming into play. So that ideas will be coming into our discussion. We'll do that. So let me just tell you that this is the fourth class in the topic, as you know. This is me. Anything, any problem you see, I can see my mail ID, email ID, phone number, etc. You can always contact me. There is also my WhatsApp number. You can WhatsApp me also. Now he is the father. I hope by this time you know him. Very common picture in almost every video lecture I've kept him. I start with him. Okay, the father of quantum ideas. Okay, so what Planck did, he explained black body radiation, which in 1900. And what I did, I first defined a few things for you. That is the basic. I started from this concept. Okay, black body radiation. So I have to define a black body and interaction of this with radiation. Radiation means it's a wave and it's an electromagnetic wave that I told you. Okay, sound wave. Okay, the electric wave. This is magnetic wave, and now we have to consider electromagnetic wave. And radiation means this electromagnetic wave. Any radiation means electromagnetic wave whose wavelength is anything between 0 to infinity, and our visible light falls is a part of it. A black body is a body, as you know, which can absorb any radiation at a low temperature, and it can emit all possible radiations at a high temperature. Ideally, its ability of absorption should be 100%, and ability of emission should be 100% also. But a black body in practice, if you look at my previous video lecture, you will see I have explained the full story how it acts. That small hole there is called orifice through which radiation comes in. If it comes in, it suffers multiple reflection. Each reflection means huge absorption, because all the inner walls are coated with the lamp black, whose absorption ability is high, very high. So as a result of that, each reflection means huge absorption, and ultimately you get an absorption ability close to 99.9%. You cannot ever reach 100% because of that red line, because of the practical losses. So what was done in the experiment of black body? This was heated. Okay, this black body was heated. If you heat it, by the definition of black body, it is expected to emit all types of radiation of all possible wavelengths. Now, what was done at this end? An experiment was done. Energy corresponding to each and every wavelength was measured and one plotted, and that graph is obtained, which you can see at the top of the screen. Now, the graph obtained has got a typical nature. Initially, it increases with wavelength, finally decreases with wavelength, and in between it passes through maxima. And now the problem is that it is not falling into our known graph nature. Now, what I did particularly last discussion is that these are the various temperature cases. If you heat it more, you generate more type of graphs. Okay, very similar graph. Nature does not change, but obviously energy emitted becomes more at a high temperature, and also maximum gets displaced. So that's a different story. I mentioned it as with displacement law, but our main objective was to discuss this idea. Okay, please see. There is what is the total. Suppose I wish to know what is the total amount of energy emitted by the black body. Then how do I get it? Okay, I wish to know this. What is the total energy emitted by the black body? How do I get it? Who is going to give me the total energy emitted by the black body? Okay. The idea is that you can get it. I can get it. Okay. If I know the suppose if I calculate this, if I add energy corresponding to each and every length emitted. So that means because it's a graph, continuous graph ending ranging from 0 to infinity. So if you wish to know what is the total energy emitted because of the emission of all possible wavelengths, so basically you have to add those e's, u1, e2, e3, 45, etc. And then practically meaning is that you are adding, you're summing over a continuous path, which is an integration. So your problem is that you can only integrate if you know the functional form of E lambda, as I have written there. Question is that Do you know this? Do you know the formula, functional formula of lambda? Answer is that this is not a known graph to us. We do not know the functional form of lambda. So problem is that if you don't know lambda, you can't integrate, and your experiment with blackbody addition remains incomplete. Last day I mentioned two options are there. First option is very easy, that you quit here. You don't have to take any trouble. Okay, you don't have to integrate. Syllabus is finished. But if this was the approach of the scientists, physical science cannot prosper. So what scientists did? They have taken up the challenge. They, because it is not a known graph, let us explore the form. What would be the probable expression of lambda? So if you think like this way, it seems to be a mathematical approach. Say I've got a curve, I want to get a formula. So initially, we actually started to explain it. Okay, he tried to give a formula of this energy, and this is the formula: a by lambda to the power 5 exponential minus b by lambda kt. Okay, as you can see there. Now the problem is that this graph, if you try to explain the nature of the graph, okay, it is only partially true. Okay, it is only true over this portion of the experimental curve. Okay, it is only true over this portion of the experimental graph where there is a quick fall over this region. But problem is that this expression of E lambda actually, it is expected to give the, okay, this curve is expected to produce or expected to explain the full experimental graph starting from lambda is equal to 0 and maybe lambda up to infinity, or theoretically up to very very high lambda. So it is only partially true. So ideally this formula reproduces a full graph, which is not happening. So as a result of that, we have discarded it. Okay. Now then, obviously another question comes into business. Okay, we are discarding it. Okay, fine. But is there any other problem with it? Problem was identified by two persons, Raleigh and Jeans. Raleigh Jeans noted down that the approach of when you try to write down equation of a graph, you may just take it as only to fit the graph without going for too many physical significance. Okay. Now Raleigh and Jeans pointed out it. Okay, they tried to know. They noticed that Wind's idea, okay, was lacking modern physical concept. It was only given from thermodynamical point of view, which was very dominant at that time of the history of physics. So what Rayleigh and Jeans tried to do before proposing an expression of lambda, they tried to put a lot of physics into it, because whatever you ultimately you are giving a formula, but whatever you tell, whatever you propose, it should provide you some new physical insight, or there should be some physical basis of your proposal. You should keep this in mind for your future studies also. Anything you propose, if you have to, if you have to explain anything, whatever you propose, there should be some logic behind. What is the logic? Physical logic. So that Rayleigh engines tried to do, and how do you put that logic? Very simple. Make some assumption. So they have made some assumption. Assumption one is very simple. At any temperature, say T1, for example, if this is a temperature T1, this cavity is full of radiations of all possible levels. So when you heat it, this will go out of the system. Second assumption was this: the atoms which are making the walls of the cavity. How many atoms are walls making the walls of the cavity? Theoretically infinite. They thought that each atom is vibrating about its mean position. So and every atom means it has got two parts. One is a, as I mentioned the other day, this is the nucleus of the atom, and this is suppose this is the charge part. It is thought that if the atom does move, the nucleus part is static. Okay, it does not move. So that basically the vibration is taking place because of the charge part or electronic part of the atomic system. So the vibration means basically who is vibrating. Actually, these are the charges are vibrating. These are the charge part is vibrating. Okay, these are the vibration of the charge part. Electron is vibrating. The charge part is vibrating. Okay, so so every atomic vibration is the vibration of the charged part of it. And it was thought by religions they are all of them are vibrating with a fixed frequency. So the nature of vibration is harmonic. So infinite atoms, they can vibrate with infinite possible frequency. Okay, so if they vibrate with infinite possible frequency, so the entire system of the all the atoms making on the walls of the cavity, all of them are vibrating. None of them are static, and their probable energies are basically anything between 0 to infinity, because infinite atoms, infinite probable energies are possible. Okay, the frequency now. The idea is that if you look at the expression of energy of an oscillator according to classical physics, this is half m omega square. This is the energy of an oscillator according to classical physics. Or omega is equal to 2 pi nu. 2 pi nu. This is the expression of the omega, the angular frequency. Now, in this expression, energy of the atomic oscillator is anything. Any atom can vibrate with, sorry, frequency of the atomic oscillator is anything. Infinite atoms, it can get infinite, each vibrate with own frequency, so they can vibrate with infinite possible frequency. So the omega, the angular frequency will also can be anything between 0 to infinity. If omega b is anything between 0 to infinity, so obviously the energy of the atomic oscillator would be anything between 0 to infinity. So I've got infinite atom, they are vibrating in infinite possible energy. Okay, when they are vibrating. Now, as I mentioned that day, the last day, that every atom means like a charged oscillator now. So I've got infinite charge oscillator vibrating with infinite possible energy. Now, according to electrodynamics, as I mentioned last day, if a if I have got a charged oscillator, if I've got an oscillating charge, okay, what would happen? It is accelerated. Okay, any it's a common sense. Okay, if I've got oscillating pendulum, as a pendulum moves, okay, its velocity gets changed. Okay, when it is at uh, the highest point, its velocity becomes the amplitude becomes maximum, velocity reduces to zero. When it is passing through the mean position, velocity gets maximum. Velocity changing means it is accelerated. So if somebody oscillates, it is accelerated. So just imagine you are replacing the bob of the pendulum, okay, with a charge, just like this picture. Okay, suppose I have got a pendulum bob. So the bob is made of a charge. Now what is happening? As the pendulum is oscillating, I have got a charge is moving. So here the velocity may be zero, and here the velocity goes to highest value. So if velocity is changing, I have got a charge accelerated. So and according to electrodynamics, if you have got an accelerated charge, it will emit radiation, and whatever, so what this oscillator will do, they will emit radiation, and that radiation is going to be added to the cavity. So the atomic oscillators are adding radiation to the cavity. It's a continuous process because infinite atoms are there. They can vibrate with infinite possible frequency. As I mentioned, their energy value, they can have any energy between 0 to infinity. There is no rule is there. Any atom can have any energy, any value of energy is possible. It may be 0 to infinity. Any value of energy is possible. So they are okay. So there is no reminder. There is no rule. If you follow the classical idea, energy of the atomic oscillator is arbitrary. They can have any energy, half omega square square. Omega can be anything, energy may be anything. No rule. So when they lose energy, so they can add any energy to the cavity. Okay. So they can add any energy to the cavity. So they will be adding any energy to the cavity. And so basically that energy is being added to the cavity. All of them are adding energy to the cavity, and some of them might also take the energy from, suppose you are heating it from a temperature T1 to T2. So now it is at a temperature T1, it is heated to a temperature T2. If you heat it, so what would happen? Because of heating, they will be also absorbed. So ultimately, this dynamic equilibrium is there, so that the cavity is full of radiation of all possible frequencies. Okay, so it's jam packed with frequency. Any atom can have any energy. No rule is there, as I mentioned time and again, and so they can lose or take any energy, and ultimately it is always full of radiation. It is a very simple idea that was presented by Legends, that the atoms which are, just repeated, atomic oscillators are all vibrating. They can vibrate with any frequency. They can have any energy. So no rule is there. So they can give and take any energy, so that the cavity is full of radiation. So ultimately, he has given a formula like this. Last day, in last lecture, I told you this formula. has got some needs some correction, because if you look at the formula of religence, okay, you see this is very good at high lambda over this region of the graph. Large lambda means if you have got increased lambda, the lambda should decrease, which is happening here. So it is corroborating. But problem is that, okay, problem is that over this region here, if we increase lambda, E lambda is expected to grow. But here in the expression, as lambda is in the denominator, it will always tell if you increase lambda, E lambda should drop. So it's a violation here. And the situation becomes pathetic, more pathetic, as you get into the lambda close to 0. If lambda goes to 0, then this expression at lambda goes to 0, E lambda, according to this theory, is going to infinity, as is shown in this graph. But experimentally, it is approaching 0. Okay, it's a Himalayan blunder that has been committed even after all those new ideas. So ultimately, again, you could not get the right expression of E lambda because it is not explaining the full exponential graph. I can only accept it if it can reproduce the full exponential graph. Okay. So again, reagents, in spite of all those hopes, all those new concepts, the atoms are oscillating, they are vibrating, they are like charge oscillator. If a charge oscillates, it loses energy. Okay, with all these concepts they tried to explain, but it is again it is partially true. Okay. So now obviously we need correction. Now that problem that is happening in the low wavelength region, low wavelength means ultra close to ultraviolet region, this problem happening here, that theory tells me it will go to infinity and experiment tells me it is going to be 0. In literature, this is called ultraviolet catastrophe. It's a very common examination question. What is ultraviolet catastrophe? Then you have to show this mathematics. So ultimately, what ultraviolet catastrophe is doing, it is making our life more difficult. We do not know the expression of E lambda till now, so we need further correction. Okay, so how do I correct? Now Planck comes into business. What Max Planck did, okay, again, his job is simple, again, is to propose a new formula of lambda. Earlier, we have told you the proposal of reagence and proposal of wind. Both of them are not good enough to explain the full the graph. They are partially right, but I need a formula that will explain the full graph. So here Planck comes into business. What Planck did, he did rigorously looked at the assumption made by Rayleigh and James. And based after looking that careful visit, they have made few some change in the idea of, that they incorporated. So what Planck did, he has taken up the first two ideas as that of Rayleigh James. That cavity of black body is fine, it's full of radiations of all possible wavelengths. And who is supplying the radiation? That is also right according to him. The atoms which are making the walls of the cavity are all vibrating about the main position, and that vibration means only the charge part is vibrating. So every atom is like a charge oscillator, and if you make a charge to oscillate, it will lose energy to the cavity. Okay. Main contradiction between Planck and Rayleigh came in this picture. If you look at the picture, that it is energy, you say I've got a pendulum oscillating, and this is something I was telling you a few minutes back. There is energy of the simple harmonic oscillator there, half of omega square is squared. Now the if you have got infinite atoms, their angular frequency, each vibrates in its own frequency. So the value of omega is basically what there is 2 pi into frequency, can be anything between 0 to infinity. So as a result of that, energy of the atomic oscillator could be anything between 0 to infinity. Okay, any value of energy is possible. They can it is anything between 0 to infinity. Okay. Now Planck contradicted that. Planck told energy of an atomic oscillator should not be like this. There should be a rule here. This is absolute indiscipline nature. Okay, what should be the energy of the atomic oscillator? Okay, any value is possible. No discipline is there. Now Planck contradicted it. He told that energy of the atomic harmonic oscillator will not follow this classical formula. Okay, change is needed. Okay, so some change is needed. What Planck thought in his third assumption that energy of the atomic oscillator is not this formula. Okay, they made an assumption that again the pendulum is oscillating. But according to Planck's contribution is this. He told that energy of the atomic oscillator should be multiple of a quantity called h nu, okay, the quantum of energy. So what Planck is doing is telling that okay, the energy of the atomic oscillator is not arbitrary. It should be something discrete, something specific. It should be multiple of a quantity called h nu. And h nu is called quantum of energy. It's a very important idea. It's a very important idea because this is the birth of quantum idea. Somebody in the earth is telling energy of an object is not arbitrary, it is discrete. Earlier it was people were happy with classical physics, that energy of expression half of omega square square. But we are not happy. Planck is not happy. He's telling energy of the atomic oscillator is not arbitrary, it is multiple of a quantity called h nu. Okay, h nu is called quantum of energy. Now the question is that, so therefore every atomic oscillator has some specific energy. Now if you look at the picture, suppose n is 1, so energy of the atomic oscillator will be 1 h nu. N is 2, 2 h nu. That means 2 times E1. So energy levels E3 may be 3 times E1, E4 may be 4 times E1. Now the idea is that because of the formula of Planck, that energy is discrete, it is multiple of a quantity h nu. So what would happen? This may be the probe energies of the particle. Okay, this is according to the Planck's idea. Energy of the objects are discrete. What Planck is doing? Okay, the earlier idea was that of Rayleigh's, that any atom, if you look at the picture, according to Rayleigh's, all energies were allowed. According to Rayleigh's, there is no rule for that. All energies are allowed. Anybody can be okay. All energies are allowed. According to this is the idea of Planck. Sorry, this is the idea of Rayleigh's. No restriction is there. Now Planck told this is not possible. The energy of the object should be discrete. So that means suppose h nu, it all depends on the value of h nu. Suppose h nu is say 1 electron volt. So the energy of the atomic oscillator would be like 1 eV, 2 eV, 3 eV, and 4 eV. These are the proper energies of the atomic oscillator. Okay, this is multiple of the quantity h nu. H nu is, so that means if h nu is 1 eV, like that. So there will be no atomic oscillator with energy say 1.325 electron volt. There will be no atomic oscillator with energy say 2.73 electron volt. There will be no atomic oscillator with energy like 3.56 electron volt. There will be no atomic oscillator with energy like 4.23 electron volt. It's not like that. Energy of the atomic oscillator has to be something very specific. It is multiple of the quantity h nu, as I mentioned there. Okay, so that arbitrariness is being removed by the Planck. And what Planck is doing, he is bringing a history now. He is telling that energy of the object should not be arbitrary. It is some discrete values are there. So suppose I have got 10 in a container, or suppose I have got 5 atomic oscillators. So what should be the energy? Okay, either 1 eV or 2 eV or 3 eV or 4 eV, like that. So they, okay, so that is, he is telling that energy is discrete. Now later on everybody followed Planck. Okay, in Einstein, Planck told it in 1900. 5 years later, Einstein utilized that idea. Energy of the that is coming from a source is discrete. It is coming discretely, and that each discrete energy, or I should say energy packet, is called a quantum of energy. Okay, now that is called the quantum of energy. Okay, Mm, this discretization process. Okay. Now, what it does actually, these are the probable energies of the electron. Now, it does another wonderful thing. 1, 2, 3, 4, as I mentioned. Or suppose you make say H2 is equal to 0.5 electrons, so energy will be like 0.51, 1.52. So that means there will be no atomic oscillator with 0.7 electron volt, no atomic oscillator with like say 0.85 electron volt. Okay. So energies are arbitrary according to Rayleigh's, and Planck is telling no, it should be discrete. That is the contribution of Planck. That energy is discrete. Later on, everybody followed Planck. Bohr followed him. Bohr also told the same thing. energy levels, if that is an electron here we are talking about, energy levels of an electron in atoms are discrete. The same idea is there. So now, if an suppose if an atom is trying to, if you look at the picture here, so lowest of the, suppose H is 0.5 electron volt. So in this picture, lowest energy is basically zero point 0.5, and highest energy is like 2 electron volt. So what would happen if an atomic oscillator now tries to come back, suppose from this state, 1.5 electron volt to ground state? Then how, what is the process? Okay, 1.5 to zero point 0.5 electron volt. Okay, so if it tries to get down, it is lose a bit of energy. Okay, it will try to get down, it will lose a bit of energy. So if it is trying to get down from 1.5 to zero point 0.5, how much energy it loses? 1 electron volt. If it's trying to get from 1 electron volt to zero point 0.5, how much energy it loses? 0. 0.5 electron volt. If it is trying to come down from 2 electron volt to zero point 0.5 electron volt, how much energy it loses? 1.5 electron volt. So you see, they're losing energy in the units of h nu, or zero point 0.5 electron volt. If you don't understand, okay, let me just again tell you. So what you are doing, if suppose there is an electron at 1 electron volt, if it comes down here, how much energy it loses here? 1 into minus 0.5 is 0.5 electron volt. So according to my description, this 0.5 is basically 1 quantum of energy. Okay. So now suppose I am talking it. So if an electron now comes from say n equal to, so idea is that this, if an electron now comes from, suppose an electron is here and it wants to come down here, so it will lose a bit of energy. How much energy? Suppose this is 1.5 electron volt, this is 1 electron volt, this is 1.5 electron volt, this is 2 electron volt, like that. So if an electron is coming down, how much energy it loses? It is losing the zero point 0.5 electron volt energy. So we consider, suppose this is equal to say 0.5 electron volt. Okay. Now if it comes from here to here, how much energy it loses? 1.5 to 1. So it will lose 1 electron volt. So if it comes from here to here, okay, how much energy it loses? So 2 minus 0.5. So it is losing energy of 1.5 electron volt. So you see, they are losing energy in the units of 0.5, 0.5, 1, 1.5. So this statement that energy of the atomic oscillators are discrete, fine. But you see, if they lose energy, that is also happening in the units of h nu. Because energy levels are discrete, even if suppose it is losing an energy, say 0.2 electron volt, it may lose, but nowhere to go, because next energy level is in the multiple of h nu. Okay. So if it is living at 1 electron volt, it only has to get to 0.5 electron volt. If 0.5 is the, it's not like that. So basically what it is doing actually, it tells you the story that therefore when those electrons are getting down to lower energy states and losing energy, so that loss of energy, and also there may be some of them may be taking energy, that is also possible. That loss of energy, suppose an electron is going from here to here, so how much energy it has taken out? It is equal to 1 electron volt energy. Okay. If it goes from here to there, how much energy it loses? 1.5 electron volt. You see, therefore, The atomic oscillators, okay, they are losing energy, fine, but they're losing energy or they are taking energy in the multiple of say h nu or zero point 0.5 electron volt. And that is the contribution of Planck. Planck is telling energy of the atomic oscillators are okay, fine. Energy of the atomic oscillators are not arbitrary. It is discrete and it will multiple of h nu. An important issue is that if they now try to lose energy, that will also happen in the units of h nu. If they now try to absorb energy, that will also happen in the units of h nu. Okay, based on that, Planck actually proposed this new expression. So Planck made four assumptions. First are two are similar to reagents. The cavity is full of radiation. Atoms which are making the walls of the cavity are charged harmonic oscillator. Now, third assumption is the new contribution of Planck. According to the earlier other theory, they thought that they have taken a classical approach. Okay, that energy that the energy of the electron will be arbitrary. Now, Planck told energy of the electron should be discrete, multiple of a quantity called h nu. Okay, they should be discrete. Okay, multiple of h nu. Okay, so if they lose energy or they take energy, that will also take place in the units of h nu. Based on that, Planck got that frequency expression written there. This expression, okay, this frequency expression they got it. Okay, this frequency expression Planck got it. Okay, you can see there. This is very beautiful. Okay, and this expression was converted into wavelength expression using this formula C is equal to nu lambda. Okay, all the news in the initial equation, okay, was converted into lambdas. Now that will become the equation of Planck's law in terms of wavelength. Okay, so whatever you see on the screen, it is the proposition of Planck in respect of the new expression of energy that will come out of Planck, because Planck is also thinking and he is giving you some new concept at least, that energy of the energy of the atoms are discrete, they are losing or taking energy in units of h nu. The first thing is that you get that energy the expression in terms of initially in terms of frequency using c equal to nu lambda. You can now always convert in terms of wavelength that you can see on the screen. But point is that okay, fine, I have got the expression of lambda. So what is your next? What do you feel? What is your next job going to be? What is your next job? Your next job is to judge whether it is a right expression or not, correct expression or not. Unless and until you confirm it's a right expression, unless and until you get to know it's an expression, because an expression will be regarded as the correct expression, which will be explaining the full graph with a lot of physical background. Now, Planck has given the physical background that you know. Now you have to judge. Sorry, you have to judge now. You have to judge now whether it is the right expression or wrong. So now I will be doing a bit of calculation. Okay, then we do it directly by hand and show you that how helpful is the Planck's law. Okay, can you get all those? Can you explain it? So let us get it. Okay, let us get it quickly. Switch off my video. So this is the expression of lambda. So Planck has given the expression in terms of frequency. Okay. In terms of frequency, the Planck law is this much. 8 pi h nu cube by c cube exponential c by kt minus 1. So what shall I do now? I will use the formula c equal to nu lambda. Nu is equal to c by lambda. Okay, or d nu is equal to c by lambda squared d lambda. You get a minus sign here, but it has got no meaning. It only tells that if your frequency goes up, wavelength should drop, or it's like that. Okay. So if I do this, this will be now an expression of energy in terms of wavelength that you can see on the screen. It will be 8 pi. If I replace nu cube, it will be like 8 pi h c cube by lambda cube by c cube, and d nu is c by lambda square d lambda exponential h c by lambda k t minus 1 gives you e lambda d lambda is equal to 8 pi h. C cube will cancel. One of the c will be there. Lambda to the power 5 d lambda exponential h c by lambda k t minus 1. So this is the expression of energy. So now, by comparing, I can remove d lambda from either side and I can get an expression of d lambda only. That is 8 pi c by lambda to the power 5, 1 by exponential h c by lambda k t minus 1. So this is a Planck's law in terms of wavelength. So now, what is my job? My intention is to explain this experimental graph, as you can see here. Okay, this is the experimental graph of black body radiation, which is the variation of energy emitted against the wavelength. So I have to exploit this expression of E lambda to explain this full experimental graph. So how do I do it? I'll start where the problem of Rayleigh is faced. I'll start with lambda equals to 0. So this is my graph, experimental graph. So my initial problem began as lambda was going to 0. So this is where ultraviolet catastrophe was taken place. Okay, lambda is going towards a smaller value. Okay, because here only the Planck that contradiction came. Okay, Rayleigh engine told it will be going to infinity. Okay, and actually experiment is actually to the left of maxima, it is going towards 0. Now this is the expression of the Planck's law, as you see here. E lambda is equal to 8 pi hc by lambda to the power 5, 1 by exponential hc by lambda kt minus 1. Now I have to expand e to the power series, considering e to the power, I hope you know, e to the power x is 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. Now in this expression, you may regard hc by lambda kt is like the x. So you can write down e lambda in this way. E lambda is therefore 8 pi hc lambda to the power 5 1 by exponential hc by lambda kt. There can be written it in this like this way. So this will be like 1 by hc by lambda kt. Okay, you can see there 1 by hc by lambda kt plus hc by lambda kt square by 2 factorial plus hc by lambda kt to the power 3 factorial plus hc by lambda kt to the power 4 factorial plus hc by lambda kt to the power 5 factorial plus hc by lambda kt to the power 6 factorial, and this is an infinite sum. This is going to continue and and it will be subtracted with minus 1. Minus 1 will be there. This is the minus 1. So ultimately, if you look at the picture now, you see 1 and 1 will cancel. So now I can get this lambda 5 inside. So we are trying to explain this region. Lambda goes to 0, where the ultraviolet catastrophe has taken place. So if you get lambda 5 inside, it is 8 pi hc. Lambda 5 inside means it is hc by kt, lambda 4, hc by kt square by 2 factorial lambda 5 and lambda squared, it will make it lambda cube hc by kt to the power 3 lambda cube in the numerator, lambda square by 3 factorial. Next one will be hc by kt to the power 4 1 by lambda by 4 factorial, because lambda 4 in the denominator multiplied with lambda 5. Next term would be how much? Next term would be this much, as you can see here. We see by kt to the power 5, you see lambda 5 in the numerator multiplied with lambda 5, so it's constant 1. And next one is very important. Lambda is in the denominator, so hc by kt to the power 6 1 by lambda 6 in the denominator, lambda 5 multiplied. So if you take the very next term, it should be like hc by kt to the power 7 by 1 by lambda squared 7 factorial and so on. So this is the expression. Now what shall I do? I am doing it for this region. Lambda is going towards 0. So if you now put a limiting case now, limit lambda goes to 0. If you put limit lambda goes to 0, this term goes off, this term goes off. So almost all the terms involving lambda as a multiplier now is going off. This can't change, this is constant because no lambda is there. Now here you get 1 by 0. So if you look at the expression now, your expression of limit lambda goes to 0 lambda is therefore 8 pi c. There are few zeros, a constant. Now here I am getting constant 1 by 0. Constant 1 by 0 square. So this is nothing but something by 0 like this, which is no meaning. So it is, this equation is therefore, and this will continue. This equation is therefore becoming like 8 pi c, constant 1 by 0 means infinity, like this. And something by infinity means it is going to 0. 1 by 0 means undefined. So ultimately what you notice, that as E lambda is approaching 0, what you notice, as E lambda is approaching 0, as lambda is approaching 0, E lambda is also approaching 0. And which is the observation of the experiment, as actually to the left of maxima, as you can see, as you are approaching, you are reducing lambda. If you think in this way, as it is going towards 0, your E lambda is also going towards 0. So you see, whatever you see in the experimental curve and whatever Planck is telling, both of them are in right, they are in agreement. So basically, Planck is successful over this portion of the curve. So ultraviolet catastrophe has been removed. Now let us go for some more region, because you see again the curve is partially right, to the left of maxima, I should say. Now I have to tell you what is going to happen here. Say for example here, lambda is very high now. Then how do you explain the situation? Can Planck's law reproduce that? So let's judge it. So same old story. If you try to explore it, the situation would be like this much. That this is your experimental graph, and we are now considering the right of lambda maximum. Here what you notice, lambda is very high, so it is showing a downward nature. Now can Planck's law explain this portion? There is a question. Now Planck's law, as just we have gotten, is like 8 pi c lambda to the power 5 1 by exponential hc by lambda kt minus 1. So now what you can do, just like the way I can expand it to the power series. It is like 1 plus hc by lambda kt plus hc by lambda kt square by 2 factorial hc by lambda kt cube by 2 factorial and so on. and there is a minus 1 also. So this blue line is the expansion of e to the power series, and this is the minus 1. Again, these two will cancel. So this is the expansion of e to the power series. Now the common sense is this. If you look at the expression, lambda is large. So if you look at the ratio, HC by lambda in the denominator high means it is low, suppose 0.1. Now if you take the square of it, okay, it will be further lower, it is like maybe 0.01. If you take the cube of it, maybe 0.001. If you take a fourth power of it, maybe further less, 0.0001. So what you are doing, this is contributions are becoming smaller, 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 smaller. So higher order terms are becoming less and less and significant. So if you, even if you add that, so what you are doing, you are adding it to 1. So it is like 1 plus, you are adding zero point 0.1, zero point 0.01. So what you are doing, you are adding this term. You are adding one more 1 at the end of this. So basically, contribution of higher order terms is almost meaningless. So even if you add them, it remains close to 1.1. Okay. So for large lambda, that is the case we are now dealing with. This is a prescription. In the expansion series, lambda large means this HCO lambda getting small. So what is happening? So all these higher order terms are becoming smaller and smaller. So these terms are all very small and neglected for the further discussion. We will actually only stick to HCO lambda kt. You may ask me why you considering HCO lambda kt. That is also low. But if I do not consider it, that means my e to the power expansion is is equal to 0 because it will become 1 there only. But I know e to the power expansion is non-zero. So to implement that, we have considered the we have HCY lambda it is like this. So now, if you look at the expression of lambda for large lambda, it is by C by lambda 5. Lambda kt by AC. Now AC's are gone. Both the AC's will be cancelling each other. Okay. One of the lambda will be cancelling. So you get 8 pi kt by lambda to the power 4. Now if you look at this expression, it tells if you increase lambda, E lambda should decrease, and which is happening here. So you see again Planck's law is very successful here. And another thing you notice, this E lambda is equal to 8 pi kt by lambda to the power 4 is okay, is nothing but 8 pi kt by lambda is nothing but the Rayleigh's law. So now you are basically answering two questions. You are getting Rayleigh's law out of Planck, and also you know Rayleigh's law is valid here. So Planck's law is also valid here. So you already explained this portion of the graph to the left of maxima. Right hand side also partially explained. Partially explained. Now you consider this region. And lambda is is low. Okay, little bit lower. So in that region, then how do you reproduce the graph? So what shall I do now? Okay. Again, we consider the moderate lambda value, lambda small. So let us revisit the experimental graph. So this is my experimental graph. We have explained the Planck's law for the left of maxima. We have explained the Planck's law for the right of lambda, so it is very high. Now we have to consider this region. If you look at the expression, this is my Planck's law. HC by lambda kt minus 1. Now, as I mentioned, e to the power series will be again expanded exponential HC by lambda kt. How the expansion? It is like 1 plus HC by lambda kt plus HC by lambda kt square cube and so on. okay, and so on. Now come to the business. You see, I am considering lambda small. So what about HC by lambda kt? This is going to be a large term. So this is going to be a large term now. Now if you take the square of it, HC by lambda kt square, so even larger. If you take the cube of it, so it is becoming more and more larger. So if it is, for example, this is 10, don't consider 10 will be the value. This will be 10 square. So this will be now 10 cube. So if I choose another value, so the fourth part of it, okay, so it is like 10 to the power 4 and so on. So it is like this summation, if you put those values, it's like 1 plus 10 square, 10 plus 10 square plus 10 cube plus 10 to the power 4. So it's a sea of numbers. It's a huge number. So this exponential term, therefore, this exponential term for small lambda, okay, this is becoming a very huge term, very high term. So a sea of numbers. So from that sea, if this one is like the one bottle of water. So that means from this huge number, it's a huge number, it's a very high number. From this very high number, if you subtract one, it remains the same high number. It remains the same high number, okay. So basically what is going to happen, so even if you subtract this minus 1, it remains the same. So the expression of E lambda is therefore 8 pi c by lambda 5 divided by this much. So now this is restricted only to this. So therefore we can write down this in this way. 8 pi c by lambda to the power 5 exponential minus h c by lambda kt. Now we may regard this constant 8 pi c as some constant a. So therefore my expression of E lambda is becoming like a by lambda to the power 5, and we may consider this constant as some constant b. It is becoming exponential minus b by lambda kt. Now I hope all of you can recognize this law. This is nothing but Wind's law that I presented you initially. We obtained it from Planck, and we know about this region Wind's law is valid. So Planck's law is valid here for small lambda maximum, left of lambda maxima. To the right here it is valid. For this region also it's valid. So it's valid for low lambda. Lambda is very low, goes to 0. It's valid for high lambda. So obviously we are in a position to accept the expression of the Planck's law because it is explaining my full experimental graph. So if we now get back to the PPT, if we get back to the PPT, so we have explained the full experimental graph. So obviously we are in a position now to accept Planck's law. Okay, but our job is due. So if you have got Planck's law, we have removed ultraviolet catastrophe. Okay, you can see there we have removed ultraviolet catastrophe. That as lambda goes to 0, okay, E lambda goes to 0. We have produced Rayleigh's law, we have produced Wind's law. Now, whatever with the discussions I have done here, these are very, very important for your examination purpose. Okay, because 3 deduction I did. First, write down Planck's law. That deduction is not included in course. You utilize that to explain the graph. How do you explain? You explain the problems. First problem, explain the removal of ultraviolet catastrophe. Second problem is that if you take care of the first issue, you are explaining to the left of maximum. To the right of maxima, you explain the lambda high value case, lambda low value, moderate value case, like that. Okay, if you do that, then we can judge the full experimental graph, and which is happening with Planck. So you accept it. So obviously you are now in a position to do that pending job because you have got lambda. So you can now calculate what is the total energy emitted out of the black body, because that is where our problem started. But I will do that, but I hope I should do that in the next class. Thank you. Okay, just for information, again I tell you, if you have got any problem, if you can't understand me or my words, you should feel free to contact and consult with me. Okay, so that's all for now. We'll meet in the next video.
Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together, it's so beautiful. You and me, we meant to be in the great outdoors, forever free. Sometimes you need to go and take a step back to see the truth around you. From a distance you can tell